Let's see if that works. Come on, little YouTube. What is this about?
I'm just realizing again how desperately I need a haircut. I look like a grad student.
I'm still jealous.
Don't worry, I'll catch up.
The hair.
Yeah.
I will definitely catch up.
All right,
Just,
all right.
give me a year.
I'm sure there's
a miracle cure out there somewhere.
Well, see,
it's called a Bic razor.
That's how I know there's no oh, we should be going live. Yeah. I don't know why we're live though. Weird. Okay. It went straight into, I didn't click start the stream. Oh well. Weird. So Nancy, we're live now in theory. If you want to go. Bye, Nancy.
Bye, Nancy.
Toodles.
We'll miss you.
All right,
She'll be back there laughing at us.
Let me rearrange the
screen
now.
Absolutely.
This almost works.
You can see half of my face.
Yeah. And then I'll make me smaller.
That's okay, Nick. Earlier he had cut the top of my head off, so.
Yeah.
I worked so hard to get centered. Yeah.
And then this is the layout, I guess. Got to be careful though. I don't have a lot of space. And then once Andrey is wrapped up, I'll be able to I'll rearrange again. Yeah.
Very narrow margin for Fraser there.
Well, but then I would lose you because I can't, like, if I could, I would trim the excess space to the left and the right of all of you, but that's just like so much work. I don't want to do
Are you gonna pull up our slides and share them or what?
No. So
we're not having slides?
We can. Here's what I'll do. I'll turn
I'm not stressing that. I'm just asking if that's what you were gonna do.
Yeah, so what I'm going to do is I'm turning on the screen sharing. And if you want to, you can screen share. But
that sounds painful.
It's right.
I actually don't have them up, so okay.
I mean, I can get to them, but that's gonna be like a whole thing, isn't it? Like,
nope.
I don't need them. I can just talk about what they're supposed to look like.
Yeah, we can. Yeah, that's fine.
We have like a vivid imagination. So
yes.
I think people can, and in fact, possibly, the imagination is sometimes better than, little red blobs. So.
Okay, quick, everyone. Picture an aurora, but pink.
I want to. Did
it's in the slide deck.
Did anyone hear if the torrid meteor shower overperformed this year?
I have not seen anything from Peter, who would have told me if they'd had some really cool outbursts.
Yeah, David was tracking that, and he said that it's in like a resonance. So the torrid meteor stream is in resonance with Earth, and so X number of years you get a boost because it's coming from Comet Encke, I think. And so normally the torrids are the lamest meteor shower of the bunch. They're 5 meteors an hour. Like that's like background meteor shower level. But
I think that's closer to 2.
2 is back. Yeah, that's what I mean, right? Right. While the Perseids are say 30 to 60 an hour, and the Geminids are even better. But
yeah, I have the website open for the new meteor shower website that we did for SETI, but I have not figured out how to wander through it yet. So
apparently I'm a little quieter than the rest of you, so I'm going to make you quieter to compensate.
Oh.
So let me know if that works.
Can't make himself louder. Got to make the rest of us quieter.
Yeah.
No, so we do actually have the Leonids to look forward to. In the colder climes, we can all go out and freeze.
Yeah. Yeah. Are they going to be okay this year? I mean,
I don't know.
I just keep remembering.
What are they again?
November.
November, yeah. But like,
Fairly soon now,
I
actually.
mean, do you
Yeah.
remember the 98, was it 98, 99 Leonids? There was like 3,000 an hour. It was ludicrous. Like,
Yeah,
what a
and then
second.
another time when I was still living in Massachusetts, I went out. I think it was maybe then or a few years later, and it was freezing cold. But I was determined to count these things. I mean, I worked at Sky and Telescope, right? And I needed to know about this. So I, at about 4 a.m, found myself laying on the hood of my car with the engine running with a blanket wrapped around me, just waiting to see these. And it didn't turn out to be as good a storm as we'd hoped.
Yeah. Yeah. So I feel like it was 99, 2001.
Maybe that's when it was.
Yeah. It was
I'd
around
say
that
01,
time.
02, and 03 had some pretty good meteor showers. I
Yeah,
know
those
'cause
did.
That's
Yeah,
when I was an
yeah.
undergrad.
Yeah, maybe it was the '01, and I was in the middle of Vancouver, and I went and just found a underpass that I could be under a
Yeah.
shadow from the city lights, and I looked up, and it was raining meteors. It was just meteor,
Yeah,
meteor,
yeah.
and it couldn't have been a worse viewing condition. And then
I was an undergrad about half an hour outside of Philly, so we pretty much packed up some telescopes and drove into Amish country.
all right,
That was a good meteor shower.
all right, I'm making you all
Out by
quieter
Lancaster.
again. I can also just get a lot closer to my microphone, everybody. Okay. All right, I made you guys all a little bit quieter again. That's weird, though.
Maybe we're all just being loud, just to spite you.
No, there is a problem with my audio. Okay, does that fix it? Everybody let me know if I got louder there. I just went from mono to stereo. So
I don't think you changed at all.
Yeah, I don't
Doesn't sound different on this link.
Yeah, I don't think I would have changed. Okay. The Yeah, all right, people are going to have to let me know. The problem with my microphone is it's stereo, like it's an actually stereo microphone, but the audio software can't handle any difference. Yeah, same volume, just in my left ear. Okay, yeah. Right. So that's what happens when setting it to stereo, is you only get sound in one ear. So there you go. All right. We've reached the 5-minute mark. Enough of this shenanigan. Let's get cracking with this week's episode. So here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, November 9th, 2022. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about plants in space, hydrothermal vents, just like Europa, probably. Where did Earth get its water? Oh, I should just go with the original title, shouldn't I? Psyche mission, why? Psyche was almost canceled, and what will we learn? Why does the moon turn red during a lunar eclipse, and why can auroras turn pink? Joining me this week, we've got Dr. Nick Castle. Hey, Nick.
Hey, Fraser. How's it going?
Good. We've got Beth Johnson. Beth.
Hello, Fraser.
And we got Carolyn Collins-Peterson. Hey, Carolyn.
Hey, good evening. How are you doing?
Good. Now, before we get into our special guest, I want to give a big shout out to our good friends of the Weekly Space Hangout crew, our friends, our fans, our executive producers. So they're the ones who call the shots, tell us what to do. If you want to join that elite group, especially when the online community that you've been probably being a part of is now crumbling all around you, you can always come and take safe refuge here at the Weekly Space Hangout crew. So go to wshcrew.space and you can sign up and just be among friends, because that's what you really want, right? All right, let's get into this week's guest. We've got Dr. Andrey Vayner. Dr. Vayner, welcome to the Weekly Space Hangout.
Hi, everyone.
The question I always ask, who are you? What do you do?
So I'm a postdoctoral fellow at the Johns Hopkins University in Baltimore, Maryland, and I study supermassive black holes and galaxies.
And you are one of the rare people who's had a chance to get your hands on JWST virtually and record some data. So what were you studying?
So this is a program called Early Release Science. So this was time that was given to a select few programs to essentially test what the observatory is capable of, going into sort of taking it to the limit in terms of the capabilities from all the different instruments. And so the program that I'm a part of called Q3D, that studies quasars across cosmic time, looking at their host galaxies and their surrounding regions. And so just for reference, a quasar is essentially an actively accreting supermassive black hole. So they're incredibly luminous and you can see them over a large range of distances. And so our program is using JWST to look at their host galaxies, specifically trying to actually remove the bright quasar because often it outshines the light from the galaxy, and actually try and study the really faint emission that is surrounding it. And so I've been a part of this program for about 3 years now, and we finally have data that we can analyze and play with and publish really cool results on.
Now, are you using the coronagraph on JWST to block the light from that central quasar and to be able to reveal those galaxies around it?
So we could be using it. It just so happens that the contrast ratio between the quasar and the actual surrounding galaxy is not too bad where you would need a coronagraph. So we are not using it, but there are programs that are interested in that sort of stuff, yeah.
So I guess, I mean, you're looking back at light that's taken 11.5 billion years to reach us. How does the age of this quasar compare to the kinds of quasars that most astronomers have been studying up to this point with, you know, boring old Hubble Space Telescope?
So the age of this quasar when the light was emitted is actually a very typical point in the history of the universe where actually you want to study quasars. It just so happens that quasar activity peaks at a look back time of around 11 billion years. This is when the universe was about 2 billion years old. And so that's the peak of both of actually supermassive black hole growth, but also the peak growth of galaxies. And so it's this very unique time frame in the history of the universe where both of those things are most active. And so we're really interested in understanding what actually happens and how do galaxies and supermassive black holes co-evolve in this one particular age of the universe. So in terms of that, it's sort of typical. It's not your most distant quasar, but it's definitely a quasar in a very interesting part of the universe history.
I mean, this is like this is close to cosmic noon, right? When the universe was at its most active star form. Like, we missed the party about 11.5 billion years ago. That's when things were really exciting.
Yeah.
And so then what can you learn from these observations that you're making?
So there's a lot that we can learn. The results that came out in this study was a little bit surprising. So what we discovered was that there's actually a lot of merger activity going on with the quasar host galaxy in the system. We did have Hubble Space Telescope imaging of this particular field before, and we did have an idea that mergers might be going on. This is actually why we really got interested in this source. But we did not expect to see this many galaxies in this tiny area of the sky. And I really owe to the sensitivity of JWST. We haven't had these sorts of sensitive infrared observations before. And so the first look paper, the sort of first result that we got looking at this data was that, oh my God, there's actually more than 3 galaxies potentially in this tiny field that we're studying. So that was very exciting.
And so, I mean, one of the great outstanding questions in astronomy is, did the galaxy form first and accrete the supermassive black hole, or did the supermassive black hole form first and bring the galaxy around it? Do you think that you're going to get a sense of which direction the evidence is leading from your observations?
I would say for these observations, that's probably not going to be the case because the black hole essentially is almost done forming. Same with the galaxy. So we're actually catching the system sort of towards the end of its exciting phase. I mean, it is still an exciting phase in the lifetime of this galaxy, right? A lot is going on. There's a lot of merger activity, a lot of star formation. You have very powerful outflows, which is what we're studying now, driven by this quasar that's affecting the galaxy. But for the most part, we think it's nearing its end. To answer that question, I think you have to go a little bit farther back in time. you probably have to go when the age of the universe was below 1 billion years, maybe half of that. So, and then if you study those early galaxies, the very early supermassive black holes, which JWST will be able to do and has been actually already looking at for some programs, I think in those cases, we might be able to see how the first supermassive black holes and the first big galaxies started growing. Yeah.
Carolyn, you worked on this story for Universe Today. You must have some questions, if I recall.
Actually, it wasn't this one. It was the story about the supernova at about 11.5 billion years that was triply lensed.
Right.
So
that was today, but this one was like a couple of
That
weeks
was today.
ago. Yeah, yeah. I feel like this was you, but
Oh.
maybe you've worked on so many stories that it's all starting to just blur together. So
Yeah.
I would love to know, I guess, practically, what was it like working with JWST compared to other space telescopes out there? You know, what was the process like?
So this data set was incredibly complicated to analyze. So we actually spent the last 2.5 years prepping for this. We had to do,
Wow.
that's why I got hired here at Johns Hopkins, actually to in part work on this program and design the analysis tools for when the data comes in, so we can actually figure out what is happening. So there's been a lot of preparatory work before the data actually came in. When the data arrives, it's usually, so we got it about 12 hours after they were taken, and you can download the raw data from the archive. You get a sort of a preview of what the data looks like. So it gets partially analyzed at one of the NASA servers, but then you have to do a lot of extra steps to get it into a form where you can actually be making images, studying those images, and figuring out what is actually happening. And that took us almost the entire summer. So we got the data. So this was in middle of June.
So right
And
after
then-
it had started, really, some of the first
Yeah.
data.
So just for context, so we had the announcement, of those first JWST images, right? And the Friday of that week is when our observations got taken. And
Wow.
there are some of the first to be using this mode with the near spec instrument. And actually, this was, I believe, the second, like, very distant galaxy to be observed with this particular mode to be looked at. And so there was a lot of work that had to be done to make that data presentable. And so we're actually finally releasing at least a portion of the data that we analyzed to the community on the 15th. So of this month. So yeah, it was a lot of work, a lot of preparatory work, and then fixing a lot of other issues that were just completely unexpected. And so yeah, it was a challenging few months.
And so, like, how many you used the near spec instrument? Did you only use the near spec instrument, or did you use any of the others? And what wavelengths were you analyzing?
So we use the near spec integral field spectrograph. So this is a very special instrument that's part of near spec that allows you to take a picture in many, many, many different colors. So you can simultaneously get around roughly 37 different color channels.
Wow.
You can think of those as like little filters, right? And so each one of those tells you a little different story about the object that you're studying. So in this case, we were looking at oxygen emission from this distant galaxy. And so we know oxygen is supposed to emit a very specific wavelength, right? But it's going to shift a little bit to the blue or to the red because the gas that's emitting it is moving. So due to the Doppler effect, you're going to get that little shift there. And so with near spec, it has enough accuracy to track that. And so we can actually study the motion of the gas in the system and actually decompose it into the different components. And that's how we figured out how many merging galaxies there are around the system.
Wow.
So it's a very, very special instrument in that regard, but it gives you a very, very, very tiny field of view. It's about 600 times smaller than the diameter of the full moon. So it's very, very, very small.
Right.
Yeah.
And so I've got a question from Arjun. Is the quasar environment from this time markedly different from other times in the universe's life, like more gas available or lighter elements?
So there's definitely a lot more gas available at this point, just to fuel the supermassive black hole in the center and also to fuel star formation in these galaxies. So it's still in that phase where there is, we think, enough gas to support star formation and black hole growth for the foreseeable future. But we also are finding quasars in relatively depleted in terms of molecular gas or future star formation regions. And some of my work has focused on in the past as well.
Now, the problem, of course, with doing research, especially using a tool that answers so many questions, is it just makes more questions. So now that you've had a chance to analyze the data and you spent all that time and you've gotten a bunch of the answers to your questions, what are the new questions that you have that you would love to be able to investigate next? If they
Right.
ever
So
let you use this telescope again.
So actually, I do have a program in cycle one with JWST to study more of these sorts of systems. So we are going to do better in terms of statistics. So we looked at one now. Well, what happens when you look at 3, 5, 10, and so forth? So we are going to do a little bit more statistics and figure that out. With this particular object, what our team has really been interested in figuring out is what is the environment that it's in? Is this a group environment? Is this actually a protocluster environment? What type of galaxy will this actually evolve to in the present day, right? And so we want to answer those questions, and we hope to continue using JWST to answer these questions, but we're also hoping to use other instruments on the ground, and including the Hubble Space Telescope, which is still doing amazing work, and we do want to point it again at this field and really figure out this particular question that just arose from these JWST observations.
It's got to feel a bit like a trap almost, that you've used the most powerful telescope available to humanity to study this very specific time in the age of the universe, and nothing else is going to be able to give you more of those answers. And so you sort of generate all these additional questions, and now you just have to wait for time whenever
Right.
it can open up again.
So the thing with using a telescope like that is that you don't know what kind of questions you're going to get, right?
Yeah.
We are still doing science of the stuff that we thought over the last 20, 30 years or so, right? JWST is going to open a lot more new questions. And in the next few years, we're going to be doing brand new science with it, and trying to answer the brand new questions that it's going to bring. And you're right. There's for a little while, there's not going to be anything that can rival it in terms of sensitivity until we get probably bigger or telescopes that can study in different wavelength.
Like 5 more JWSTs.
Or 5 more, sure.
Yeah, but
yeah,
I wonder what that is. Well, that's a shame because we it's oversubscribed right now, to say the least.
Yeah. And it definitely the sense that we're feeling is that there's a lot of data coming in, and there will be for the next future, but we don't have enough people to look at all this data. So there's going to be a lot of stuff sitting on the archive, that people over the next 10, 20 years or so are going to make amazing discoveries with. So there's a lot of stuff that we just haven't really thought of, but that's sitting there and it's available to the general community.
Yeah, I think that's a fantastic point. I mean, I think people were so early in the process that the first observations are still in the proprietary period. And it's only once we get past that first year and all that data starts to dump out onto the archive servers that the entire astronomical community can start digging in and will be doing just some incredible science. Someone's going to use your quasar picture for something that you had never expected. And that's exciting.
Right. And we are already getting requests from other teams to have a look at our data and try to do their science that they want to do with it. So I mean it's already happening.
That's really exciting. Well, Dr. Vayner, thank you so much for taking the time to chat with us today. If people want to follow your work, what's the best place to do that?
So I'm on Twitter, which is just Astro Vayner, and then there's a link to my website there, which has information about all the research that I'm working on. So that's probably the best way to learn about the stuff that I'm working on.
Fantastic. Well, thank you so much for taking the time to chat with us today, and good luck. And I look forward to all the discoveries that come from you and the rest of the people working with this incredible telescope.
All right. Thank you so much for having me. It was a lot of fun.
All right. Take care.
Bye.
All right. Let me try rearranging. Let's see. This isn't terrible. Let's go there. All right. I can Yeah. All right. This will do. This will do. Okay. All right. Let's see. Nick, why does the moon turn red during an eclipse?
Well, I think that's a pretty fun question. I mean, if you think about it, shadows that you see on the ground are usually, gray or black, depending upon how intense they are. So why is it that during totality the sun turns brilliant red? Well, the answer is it's in the full shadow of the Earth, but the Earth is big enough, you've got other things going on too. Basically, what's happening is the light is hitting the atmosphere and it's diffracting like it hit a prism. Blue light bends a different amount than red light does, and red light penetrates the atmosphere a little bit better than the blue does. So you actually end up essentially projecting a sunset right onto the surface of the moon,
Yeah.
because that's the only thing that made it through the Earth's shadow. Also, the Earth is large enough that you're just bending just enough of it, refracting through the atmosphere, that it's bending the light around as well.
So I love that idea that you're getting a sunset across the entire moon.
Yeah.
If you were standing on the moon and you were looking at the Earth as the eclipse was happening, what would you see?
Well, I'd imagine it would look a lot like a solar eclipse does from the Earth, just, immensely cooler because you're on the moon.
Right. Just
the Earth is a lot larger.
That you're on the moon. Yeah.
Well, it's also the Earth is a lot larger from perspective on the moon than the moon is from perspective on the Earth, because the Earth is bigger and they're the same distance apart. So I actually, I do know the math on this. The Earth would block out the entire sun.
Oh, yeah.
Assuming it was a total Earth eclipse.
I feel like it is the Earth looks 13 times bigger from the surface of the moon than the moon looks from the surface of the Earth. So it's gigantic.
That makes approximate sense to me, but I couldn't confirm the numbers without doing
no. And like when you think
search.
There's just a fantastic image by Andrew Walker released on. Well, like, people have done this where they put the moon side by side. I want to find his picture.
Yeah, I know which one you're talking about.
Yeah, and
showing the whole sequence through.
And it shows you the sequence to the point that you can actually see. I'm going to just share the picture because it's.
Yeah, you can actually see the full Earth shadow project against the different pieces of the image.
So
like that.
I don't know if you can all see this, but
so there's actually a really cool phenomenon.
Yeah, and so there's the Earth right there, and there's the point. You can see it sort of chipping away. Yeah, just a phenomenal picture.
And so it's really as you're getting into the very dark of Earth's shadow that you're getting just the bent light that's traveled through the atmosphere. And only the red's really made it through that's hitting the moon at that point.
Yeah.
And if you don't believe me, that's diffracting like a prism. If you are really good at astrophotography, or look at the image that's in the slide deck from someone else who is really good at it, you can actually catch a little bit of a blue band right near the transition from going into totality or going out of totality. And see that blue and purple compressed in a little tiny band that disappears real quick.
And is that similar to the blue flash that you can see if you are watching the sun go down on the horizon?
No idea. I've never actually seen that.
I've never seen it either. There's a green flash and there's the blue flash. Okay. Carolyn, have you ever seen it? You must have talked about this in the past.
Just the green flash, and only for a really brief.
Yeah.
I don't think I've seen the blue.
I haven't. No, but people have. Yeah, people have definitely seen the green and if the conditions are perfect, then you get the blue, and you're just getting that last light that is being bent by the atmosphere. The wavelengths are being sent past your face one at a time, and so you get the green one, and then you get the blue one, and then the sun is totally gone, which is mind blowing. It's going to be like 900 days until our next lunar eclipse, not till 2025.
You keep saying it that way, and that makes it sound super long.
I know.
Far.
I had originally said it was 3 years, but I'm like, wait, it's not 3 years because it's March 2025. So it's not too, like, it's not safe to just say it won't be for 2 more years because we've got November, December, January, February, March. That's like 5 months, 4 or 5 months. So
think of it this way. We're halfway through a presidential term. It'll be shortly after the next election.
It'll be shortly after the next total solar eclipse passes through the United States and Canada. That's That's the part that I think is exciting. Awesome. Well,
Agreed.
I hope people got a chance to see it. If not, you just have to wait 894 days. All right. Beth, where did the Earth get its water?
So one of the theories that people keep proposing is that the water we have on Earth came from asteroids and comets that were hitting it, particularly talking about sort of late, early bombardment stuff, but continuing on to present day. And to do sort of figure out what's coming in with these meteorites that we keep finding, they're trying to figure out what they're completely composed of. You know, you can look at it and you can say, okay, well, I can tell it's this kind of meteorite, which means it's probably got a lot of this in it or a lot of that in it. But what this team at the National Institute of Standards and Technology has done has taken X-ray imaging and neutron imaging and combined them together to map on a molecular level what is in a meteorite.
Okay, I'm going to share a picture here.
Yeah, this is so cool. So what this does is it's basically depicting the overlay of these two types of imaging. So on the visual that you're looking at, the purple and the orange are iron-rich minerals, and the green are minerals that contain water in their structure. So you can actually see where these minerals are coming from. And they did this with a couple meteorites that have already had slices taken out of them and sampled, so they know what they're looking for and they know what to expect. And their results are pretty amazing. There's another one that they did that this is the smaller of the two, I think. And then there's a bigger one that they did where it's even more mapped out than this. And it's just incredible, the imaging that they've gotten through this. And now they can kind of see like, yeah, okay, these are hydrogen compounds that are in here. And that's probably a lot of water. And here's where it comes from. And now that they've done this with 2 known meteorites, the plan is to go back and start looking at other meteorites and start running them through the same process and see if they can figure out like really how much water these particular rocks have brought to Earth. So it's really exciting. You made the comment earlier about you should have gone with the original headline. So I'm going to read this because the audience deserves to know how bad this headline is. The headline is Research on the Rocks, Combining Neutrons and X-ray Imaging. NIST scientists study meteorites to explore the mystery of how Earth acquired its water. And the first time I came across this, I thought, I have no idea what this is, and I'm not sure I care. And then I started reading, and then I kept reading, and then I went, this is actually really, really cool. So yeah, they're mapping rocks.
We'll cover it on Universe Today. I'm sold. I 100%. I know. I saw it, and I just went, I don't care, and just moved on.
Yeah.
And then you see
I have the same reaction.
You see this animation, and you're like, I could watch this all day. So okay, I'm sold.
Yeah, I was pleasantly surprised as I started reading it. I'm like, all right, what is this? What is this about? Because this headline is terrible, and it's actually really cool research. So yeah, so you're looking at a map. Basically, they're mapping molecules inside a rock.
And so the gist of this really is that there are hydrogen-rich compounds, minerals inside asteroids and meteors across the solar system that were likely helped deliver the water to Earth. Do we know if the actual like molecular fingerprint matches up with the ratios of deuterium and hydrogen here on Earth? Because that's always the way that they confirm where the water came from. They're looking for that ratio of hydrogen, deuterium.
If I remember rightly, yes and no.
Okay.
There are some that have, and then there are some that haven't, and then there's also a lot of time that's passed. So and it gets a little sketchy. But there hasn't been like a smoking gun of yes, this is absolutely the case.
Like Nick, what is the current thinking on this right now? Where the water came from?
So
I was asking. Sorry, so Nick was just jumping in. Beth, sorry.
Yeah. Go ahead, Nick.
Sorry, my computer also lagged right then, which is super fun. So it's actually really, really hard to get a good isotopic composition for hydrogen within a meteorite that's sat at all on the Earth's surface. And the reason why is because it exchanges really quickly, even if it's structurally bound in the mineral. That exchange time happens within days, weeks, months. And most of these meteorites have been sitting here for many, many years. And so whatever signal was there is often just gone.
And that's why they're
This is one of
so
the really-
excited when they find those new ones that have fallen.
Yes. This is one of the great things about a fresh
Interesting.
fall is you don't have to worry as much about terrestrial contamination. Hydrogen deuterium, you're still struggling with that. That's one of the reasons why we use oxygen so frequently. It's because that takes longer to get at with those things.
That's
Yeah,
really interesting.
And this, one of the really cool things about this technique is you can actually pull out some of the compositional information, not just like where's the iron, but what exactly are you hitting with the X-rays? And the neutrons map a totally different data set, and you can do it at the same time if you're in the right kind of beamline to do this so precisely. So you can get the whole chemistry in a 3D structure without disturbing it. So this is the kind of thing that would be really neat to develop for a return sample that's completely pristine, never touched anything on the Earth.
And then you can also use that information to determine where you want to take your slices from so that you're not just carving chunks out of your meteorites willy-nilly hoping that you get something interesting. You can look at it and say, okay, if we turn it this way and we go over here,
Right, drill
we can actually get a
in,
decent slice.
just get this exact mineral
Absolutely.
that we're looking for.
Yeah.
That's really exciting. It would, I mean, can you imagine having that on Mars?
Yeah. It'd be amazing.
Yes, please.
Yes, please.
I wonder how big the machine is that they use to build that map. Like, it's got to just be like a room-sized system.
Beth, was this one of the ones that comes off of a beamline?
I'm not sure that it actually said which machines they used for it. They just
Oftentimes
said
when
what
you're talking-
technique.
Oftentimes when you're talking about this kind of precision in X-ray microtomography, you're talking about X-rays produced by a beamline. Same kind of idea when you're hitting it with that kind of flux of neutrons.
Yes.
Because that's a really good way to make it.
So they use the X-ray and neutron beams at the Oak Ridge National Laboratory and University of Chicago.
So you're talking about taking something like, well, Oak Ridge and moving it to Mars. Good luck.
Good
I mean, please do.
Yeah, if you
I mean,
can.
hey,
Not
but
necessarily literally Oak Ridge, but
Yeah.
we got X-ray diffraction down to, a handheld, carry it in your hand, walk around and scan a rock. So,
which was actually developed for Mars.
I know.
Like that whole handheld device was developed because we wanted to put it on a Mars rover, and someone had to think through. And Philippe was thinking through, how do I do this, and designed a thing.
It was his life's work. Like it was even before figuring it out for Mars, he'd been working on it to get it to happen. And then because they wanted it for Mars, he got some more money. And now you can pick up a little handheld like suitcase, like a little mini briefcase kind of thing, and crumble up stuff and scan it, and it'll tell you what it's made of right there on the box.
That's neat. That's really cool. All right, Carolyn, let's talk about plants, adapting plants to thrive in space.
Right. So when I wrote this story, I actually said, well, we all have to eat, right? And people have to eat in space. So a couple of days ago, I think it was the 6th, the SS Sally Ride Cygnus capsule took off on a Northrop Grumman mission, left Earth, and it arrived at the International Space Station. I guess they had a little problem with the solar panel, but anyway, it was carrying a bunch of supplies for the station. And there was also an experiment called Plant Habitat 3. Now that's short for, you think your headline was bad, Beth. This one's really long. It's short for a program called Epigenetic Adaptation to the Spaceflight Environment, Accumulated Genomic Change Induced by Generations in Space. So that's kind of a long-handed name for this experiment that's going to be growing plants in microgravity and harvesting them. And then they're going to bring the harvest back to Earth, including the seeds that are germinated for further study. And then once they're studied, they'll send the same seeds back up to space, along with a control group, I guess, of seeds that haven't been exposed to space of the same plant. And then the whole thing will get planted again on the ISS in the future. And they'll watch a second generation of plants grow and compare and contrast between the first generation and the second, and then they'll harvest. And it's basically rinse, lather, and repeat over and over again. So The idea is to study how living in space changes the genetic expression of the plant. So that's not that it's going to mutate, but there's some little change that goes on that would cause the plant to have a different gene expression, depending on what it's responding to. So the plant they're using is called Arabidopsis thaliana, and it's not the first time it's been sent up there. I get the impression they're using it quite a bit. It's very hardy, it's adaptable. But this time they're basically looking to see how this plant is going to change its genetics in response to space flight. Now, it turns out that the microgravity experiment is kind of stressful for plants. And so it does cause them to adapt in the way, and that's really what they want to measure is this adaptation. To get a little specific, it's kind of a process where the gene gets stimulated, it gets turned on somehow in a cell, and it starts to make RNA and other proteins, and then that causes the gene expression to change. So I don't know if that means that it's going to look any different, but there's going to be some different function of the plant after it's been in space.
The point here is that it's an epigenetic response.
Right.
So it's not like they're breeding the plants to be more hardy for space. I'm sure that experiment.
Well, that might be an outcome later on once they understand it, and then they can maybe do a little bit of, messing around with it. But it's right now they're just looking to see what the changes are, and then if for example you have a group of plants that you send up there and you're using them to eat or to make pharmaceuticals or do whatever it is you're going to do with them in space in a long-term flight, you want to understand what those changes are, because that might change the outcome of whatever you're doing, whatever you're eating, the drugs you're making, that sort of. And so if they're changing in response to being in space, you kind of want to figure out what that change is going to be, maybe even be allowed to predict it.
I mean, here on Earth, we depend on plants for so much stuff. Obviously, everything that we eat, everything that we breathe, our soil, everything is all about plants, and it is this giant free resource. The sun is turning, providing the energy. The plants are doing useful work with that energy, and we are harvesting the benefits from that. When you're in space, you have to do everything completely yourself. You've got to pipe in your own oxygen. You've got to gather your own energy, and you've got to, provide all your food, etc. Everything is done. And if we can get to this point where we can start to shift back, where we can rely on plants to do that useful work for us again in a way that's sustainable and healthy for the plants themselves, that would be really exciting. But
the interesting thing here too is that, there's a couple of things. One of them, obviously we in the plants didn't evolve in space. We evolved in this, 1G, environment where we got water and everything is just kind of handed to us, as opposed to in space where we actually have to do that. But there's some interesting analog studies that, in the original release that they sent out, where they're talking about how all of the things that we're learning about putting these plants in space may actually help understand how plants are stressed on the planet, particularly as climate change progresses. And so finding out how that stress affects genetic expression in space may also help us figure it out on Earth. So there's a nice spin-off and a nice feedback to that.
Yeah, that's really cool.
I love how often that happens with space technology and research. It's, we've used this different environment to isolate some variables we couldn't on Earth. Hey, look, that means things back on Earth too.
Yeah.
Yes.
Well, and then you also think about, whenever we start sending anybody off to Mars or beyond, these are things they're going to have to depend on. So we really do need to understand what we're sending along with them.
Yeah.
Yep.
It's not going to be like
I also think it's really neat
that they're potatoes.
Who knows? Maybe
epigenetic potatoes. Yeah.
Epigenetic potatoes. There we go.
Poop potatoes.
I think it's really cool that they're looking at the epigenetic expression. It's not genetic changes. It's just the existing genes. How are they coming out?
Yeah. It's really studying an evolution at a really small level.
Yeah.
Or a really, really tiny level.
Yeah. And amazing how life can adapt even to a situation that is completely foreign. Like, I don't know how many plants out there evolved to live in microgravity. Like, maybe plants in the ocean are kind of going through something like that. But even so, it's a fascinating idea. Very cool.
Here's
all right.
just one cool thing to think about. How does the plant know which way is up?
I always wondered
on Earth,
that
it's
too.
the gravity field. In space, it's the, I don't know.
Yeah.
Well, they do have a little microgravity, but I think, they would be interesting to know what, not exactly that they're, I don't want to anthropomorphize it, but what does the plant think,
Right.
about this
Yeah.
when it gets up there?
Yeah, I think it just freaks out and
So
it's
I,
screaming.
I know they've done experiments with like spiders to understand, because
Yeah,
how they
yeah.
design their webs is based on gravity and up and down, and so they've actually, as horrifying as that is to me, they've actually taken spiders up there and watched them build webs.
That's wonderful.
Now, Beth, you're making me wonder if they can take some dung beetles up there and see what happens.
Right.
Oh, that's a really good question.
Yeah,
Right,
yeah.
because they're
Maybe
guided. They're guided as well, huh?
Yeah,
Yeah.
yeah.
Yeah, that's
They
really
probably
interesting.
have. I swear they've taken everything up there.
Yeah, I really like that. All right, Beth, let's talk about what happened with Psyche. It's back on.
It's back on. There was some question because it didn't make its launch date earlier this year, and that was a big deal. So NASA sent a review board and said, "Go look at this and figure out what's happening at JPL and why this didn't work." And basically, what they said is that there weren't enough people. There was an imbalance between the workload and the available workforce. So they're trying to figure that out, figure out how to address it. They'll meet again early next year, I believe, to see where things are going. So they're adding a bunch of people. I think they're filling the project chief engineer, guidance nav, and control cognizant engineer positions. They have a lot of engineering positions they're filling. They're trying to do all of this. The big part of this that kind of gets really buried in the story is that this is going to delay the Veritas mission by at least 3 years. So because they're basically shuffling existing people around as well and moving them from one project to the other. So Veritas is going to kind of have to be delayed too.
So, I mean, is this a systemic problem at JPL that they haven't hired enough people? Do they not have enough budget to hire these people? Or is just everybody getting sucked into the SpaceX vortex?
It basically said that they have inadequate flight project staffing. So yeah, it sounds like it's an overall problem, and the post-pandemic work environment has not helped. And then they've lost some people who knew how to handle the organizational side of things, and so it's kind of been sort of, I think Carolyn summed it up before the show best, where it's tumbling dominoes. One thing affects another, and so now Veritas is the one that's gonna have to be held off to fix this so that we can send Psyche, which I'm excited about Psyche and I really want to see it happen.
Yeah, it's super metal.
And we have other Venus missions coming up. So
Venus.
That was terrible, Fraser.
We use that pun all the time on Universe Today. Like there could be metal volcanoes or the remnants of metal volcanoes on Psyche. How awesome would that be? Amazing.
I just want to.
Cool.
I think it's interesting that it's one of those things where they've advanced the theory that it's a planetary core. Now it's probably not a planetary core. What is it? Let's just go and send something and find out what the answer to that is.
Yeah.
So that's I want to know. I just want to know what the answer to the question is. What is it?
You are a flight engineer, there could be an opportunity at NASA for you right now.
Yeah.
And also everywhere else too. Everybody needs workers.
Yeah.
All right, Nick, what does it take to make an aurora turn pink?
Well, it turns out the short answer is a really strong solar storm. So auroras can come in a whole bunch of different colors, but the most common by far is green. And basically what's going on is the same sort of thing with cathodoluminescence. It's when typically electrons hit typically oxygen in the uppermost atmosphere, it ends up releasing light in the green spectrum. Oh, thank you. You brought up one of the pictures of it.
Yeah.
Pink is actually apparently about the second most common color to see in an aurora, but it only really happens when you have a really strong solar storm that's starting to push the magnetic field down So the high energy particles are making it further into Earth's atmosphere. And you're starting to get things like nitrogen that are glowing. So it's interesting that you're basically doing spectroscopy on what's the composition of the upper atmosphere and the, beyond the upper atmosphere, the trace amounts of atmosphere, by what's the solar energy particles that are hitting it.
Yeah.
I thought it was a neat story because it meant I got to talk physics while pretending to talk chemistry.
Right. And so here's the, so here's the thing that's important here. So this is a story on space.com.
Yep.
And they covered this pink. So this is by Marcus Varick was that first picture. And then here's another one by
this was a photographer in Norway who is looking at, he runs aurora tours. So he sees your typical green aurora all the time. And this time when he was out and set up to do photography, it turned pink, which isn't very normal to see captured. Most pictures you see of the aurora are green. Now, there have been a lot of other colors reported, and we can tag them to what likely high energy particle chemistry of the atmosphere interactions are going on. Blue, violet, orange, yellow, red, a whole spectrum of things that we know happen, but you don't frequently get to take pictures of it because it doesn't happen for long. Now, the reason why this one's cool is because there's such a strong solar activity, it compressed the Earth's magnetic field. I think space.com was being a little extremist, saying they were poking a hole in the magnetic field.
Right.
It's not really that. It's when the magnetic field gets so compressed that it starts to cut into the atmosphere. They're getting more of the high energy particles just making it through.
Right. Phenomenal. What's the best aurora that you've seen, Nick? Have you seen many auroras?
I actually did manage to see a whole bunch. It turns out early on, when I was just starting my PhD, I was living up in Edmonton, Alberta, which is high enough up that aurora aren't uncommon. A couple of times I was actually, sitting at a restaurant outside, looked up and went, there are green bands in the sky. That's not normal. Although inevitably, whenever I tried to grab friends and drive into the dark countryside, everything was gone by the time I got there.
Yeah.
Which explains why we never have good pictures of these things.
I have seen some amazing videos from Edmonton specifically. And I one time was flying across Canada from Toronto back to Vancouver Island and saw auroras above.
I would love to see it from the air.
I was above Manitoba.
I'm very envious. I've never seen one.
It was astonishing. It was like ribbons, like when you see those pictures from the International Space Station, you really get a sense that they are ribbons, like snakes that are.
Yeah, you really see this very three-dimensionality.
Yeah, exactly. And normally when you see one, you see it off on the horizon, and so you see it as this sheet in the sky, but really it is a sheet, and so you can get close to it, and if you're directly under it, then you get this ribbon that's directly above you. And where I was positioned as this was happening is I was very close to where it was happening, and so I wasn't seeing these sheets off to the horizon. I was seeing that three-dimensionality to it. The best one I've ever seen actually was here on Vancouver Island. And we got a notification that there was going to be a solar event, and so we went out to the beach, and we have a place we can look to the north, and that's like our best shot because we're like at the very bottom of viable aurora territory here, and nothing. An hour into it, suddenly, boom! The whole sky from horizon to horizon was just filled with aurora, and I captured it on my phone. Like, it was so bright and so vivid and moving so quickly that my phone could see it. And then I took a bunch of pictures with my camera. But it's really hard. Like, when you see those pictures of an aurora, it doesn't do it justice because it's so fast moving and so alive.
And one of the really cool things, if you really get to see the bands, because sometimes, if you're in northern latitudes, you can just kind of see one horizon went a little green. Yes, you're seeing the aurora, but you're not really seen it.
Yeah.
If you see the bands, they'll move like as you're watching them. They'll worm around
They
in the
move
sky.
fast. Like that's the thing
They
that
certainly
surprised
can,
me.
yeah.
Yeah, is that it feels like this flickering, writhing,
Yeah.
shimmering curtain of blue and green and purple in the sky. It is not this sort of thing that just sits there and you take some pictures of it. It is alive and quite exciting to watch. And no picture, and this I give what my point of this is, like, no picture does it justice.
Yeah.
Because
A
it's
good video can really show you some,
yeah.
but being there in person to see it is
Yeah.
just neat.
Yeah, like video doesn't have
And
the
so-
long enough exposure time, and if you take a long exposure
Yeah.
picture with a camera, then it's just a blurry mess that doesn't really
Yep.
capture what it looks like. So it's one of these things that I've never seen a picture and gone, yeah, that's what it was like, and I've never seen a video and going, yeah, that was what it was like. It's like something else that I can't describe. Yeah.
One of the coolest mistakes I made during graduate school, I set up an experiment that was going to be 2 weeks long. And the start time I set at a normal human time, the end time I set at a normal human time, like working-ish hours. I forgot that there was an important time in the middle of the experiment where I had to be in lab. So of course it's 2:30 in the morning. I have to show up at lab to twiddle a knob and watch it for 10 minutes. But as I'm stepping on my back porch to hop on my bike and bike to campus at 2:30 in the morning, I happen to glance up and there are these ice blue bands dancing around in the sky.
Wow.
Suddenly I wasn't annoyed to have to wake up in the middle of the night for a lab experiment.
Yeah, you're calling your friends to wake them up to come and check it
Oh
out.
yeah, no.
Yeah, yeah. And so
I definitely called my then girlfriend, now wife, and said, "Step outside of the building. You've lived in Canada your whole life and you've never seen Aurora. Look up right now."
right.
So she ran out of her building in time for it to be gone.
Oh, yeah. Yeah, of course. Yeah. And so Beth, you've never seen it. Oh.
No, I grew up in Colorado and Florida, Georgia, and here in California. And unfortunately, every place I've lived, it's just been too far south.
Yeah.
So I've never gotten to see one. And when I visited my sister in Minnesota, we just never had the luck of actually having one at the same time.
Yeah.
So
Carolyn?
it hasn't worked out for me.
Yeah, I've seen them. We saw the first one I ever saw was I saw them in Iceland. I've seen them over at the Antarctic.
What?
And then I watched it for about an hour on board a plane going to Iceland.
Oh.
Nice.
Yeah, we were on board a ship. It was my first lecture experience, and we were down getting ready to go past the Horn, and we look up and there's this bright glow to the south, and there's no city there. So it was Aurora.
Wow, that's amazing. So cool.
First one I ever saw was a trip to Iceland. It was a geology field trip. Spring break, going to Iceland in full snow gear and dealing with
And you
the
froze your
blizzards.
butt off. Yeah.
Yeah.
We drove down to the southeastern corner of Iceland to go hike around the glacier and look around and see, like, this is what, very raw volcanic and glaciated terrain looks like, because you're not going to see that easily much of anywhere else. And one evening we step out, this little shack that we're staying in. It's literally a bunkhouse, and there's nothing else for more than an hour in any direction. And the whole mountainside to the north of us is just outlined in green.
Wow.
It's like, okay, technically I've seen it.
I suspect we've got everybody just salivating at this point. So if you can figure out a way to go and see an aurora, like, it's going to take, if you don't live in a place where they happen all the time, what Eric Knapp is saying, I live in Alaska, so I see them all the time. But if you've not seen them all the time, plan a trip somewhere north and get one of these into your eyeballs, because it's pretty great.
Aim for solar maximum.
Yes. Yeah. Well, I guess that's the point. We are on our way towards solar maximum.
Yep.
And so they're going to be more common, more ferocious, and you got better chances. All right. Well, we've reached the end of our hour, so I want to give my co-hosts a chance to shamelessly self-promote themselves and their work. Nick, what are you working on, and where can people find out more?
I am the wandering scientist, currently in search of a better SEM. You can follow me on Twitter. You can follow me on Instagram. I'm there from time to time, occasionally spouting less than awesome opinions.
Beth.
Like where we should all leave.
I am at Planetary Pan on all the things, including Counter Social and Mastodon, because I am a social media person, so I have to learn all the new sites.
Yeah. Go
And
everywhere.
this week on SETI Live, I am interviewing my mentor, Dr. Peter Yenniskins, and we are going to talk about that very same meteorshowers.seti.org website that has been redesigned. So basically, all of this meteor data comes in and it gets processed automatically and goes up on the website. So
Fantastic. All right, Carolyn.
Well, you can find me at Universe Today and also at thespacewriter.com. I'm at Spacewriter on Twitter, and I just joined Mastodon, and I think I'm the Space Writer there. And I'm currently doing a deep dive into planets for one of my projects.
Fantastic. All right. What do I have that's interesting? So I just did an interview with the people behind Benjamin Pope, who's behind that new tree ring study about these devastating solar storms that have hit the Earth. And it was a lot of fun, very eye-opening, very unnerving. But he's terrific, and it was a wonderful conversation. So that interview is going to be showing up on my channel in the next couple of days. So stay tuned for that. All right. Well, thank you everyone for watching us here today. Thanks to all of the moderators, all my co-hosts. Thanks to our special guest, and a special thanks as always to Nancy Graziano for organizing this whole show. We couldn't do this without you. Thanks to me for engineering it this week. We will see all of you next week. Thanks, everyone.